Okay, moving on, finally out of the method section, we're gonna move on to results. So this is where you get to ask yourself, was my hypothesis supported or rejected? And note, we're not using the word proven or not. You can't prove things in science. As I'm sure you've seen, even just with COVID research going on, science is constantly evolving, more research is being done, theories are getting updated, things like that. So what we know about the world might be different than what we know about the world in a couple months or years. So we don't prove anything to be true. We either show evidence that supports some sort of theory or rejects it. So one thing we might do once we've collected all of our data from our sample and we have it in front of us and we're trying to look at it, might be to just describe what we've got. We organize the data in some sort of meaningful way. So ways that can happen are what we call measures of central tendency. So these are 3 different things that perhaps you've heard of before that help give you kind of a general concept of where the center of that data is in a way. So mean is perhaps the most common. Mean is the average. So just kind of what the overall average value, if everyone in that group had the same exact value, what would that value be? Median, however, is the middle, the halfway mark. So as a whole, if you order all of your values from smallest to largest, what value happens to land in the middle? And then mode is your most frequently occurring score, the score that occurs the most. So perhaps that's more informative, is to know when in general, how frequently values do occur. So just to go through some quick examples, perhaps we have these data of 10 OSU football scores, how many wins the team got per season. Also just like RIP the season for this fall. Sorry that it got canceled. It's for the best. Let's just live vicariously through cartoons and random examples. So OSU football record. Here are 10 data points. So let's walk through those 3 measures of central tendency. If you wanted to know the mean score, add them all up, divide by how many you've got, and that tells you that on average, they scored about 11.7 wins each year. Median, we're gonna arrange all of our values from smallest to largest, and whatever number's in the middle is the one we use. In this case, if there's an even number of points, you find the average of the 2 in the middle, and 12 and 12 is still 12. So the median number of wins is 12. And then mode, take kind of a histogram, how often each score was gotten. And in this case, 12 was the most frequent score, so your mode is also 12. But let's ask ourselves, when would you use each of these? Why, like, when is it beneficial to tell someone the average versus the mode, that kind of thing? So let's go through these 4 examples, and I want you to think about which measure of central tendency, mean, median, or mode, would you use to most accurately describe this data? What's more helpful for you if you were told descriptive statistics about this data set? So pause, take a second, think about this. Okay, so if we have grades of students in a class, I'm sure you guys, have experienced this yourself. You want to know, okay, I scored something on a particular test, or I'm got a certain score in a course. What was the average score? Was I above average? Like that's like the question you always ask. So typically, we care about the average grade in the class. Other answers, mode could also be informative. Perhaps if you have a bimodal distribution. So you've got 2 different modes. Maybe it's informative to say, okay, you had a subset of people in your class who scored an 85, but also a subset of people that scored a 50. And so that might be more informative than being like, oh, on average, it was like 65. I don't know. So it could depend. Number of arms a human has. This is fun because when I first learned this example, I was like, what? Because typically you might think that average is always the most informative, or mean. And like that generally is the case. But fun fact, the mean number of arms a human has, if you sample people among the general population, is not 2. Because if you have any individual who has lost an arm or was born without an arm, that number is then going to shrink. So in this case, the number that appears the most, or the mode number of arms, is probably more informative to say that 2 is the number of arms that a human has. Height of US males, again, on average, we tend to use a mean to talk about how tall individuals are. And then your test scores. Test scores you often see with percentiles. Anytime you see the word percentile, that's your clue that you're looking at medians. Because if you want to know, were you in the 50th percentile of your test score? That's saying, all right, if you take everyone who took that test and line them up, where's the halfway point at? What score did 50% of the people score above and 50% of the people score below? So median, cool. A couple other things to talk about is that are not measures of central tendency, but are more related to the spread of information, is standard deviation. So what this is looking at is how far the individual data points vary from the mean, how tightly clustered they might be, or how spread apart, how far they deviate from the middle value. So in this example here, we have the mean is represented always by the center, this long line that you have in the center. A small standard deviation, what you see there in the kind of pink shade, would mean that they're really tightly clustered around the mean. So most values are really similar to each other. Medium is a little bit wider, and a large standard deviation means your values are pretty far apart. They don't really cluster super well. There's a large spread. And there's what we call a normal distribution, which is just a perfectly symmetrical version of this, because data isn't always perfect. But in a hypothetical, real world, we like to think about it. Hypothetical real is totally an oxymoron. In thinking about data and modeling and thinking hypothetically about what our data should look like, we'd like to talk about normal distributions. And normal just means symmetrical, not necessarily like typical or that kind of thing. It doesn't typically result in this way. So normal distributions are bell-shaped curves, as you can kind of see here. One common thing that you might hear talked about as normal distribution is IQ. But what I want you to know about this is that half of the data is exactly above the mean and half is below the mean. In fact, you've got the same value for your mean, median, and mode. It's going to be the most common value, the number that's the average, and the number that's in the middle, which is kind of cool. And there's a rule called the 68, 95, 99 rule, which is what we get by these colored bars. So the first section, the purple section, represents one standard deviation from the mean. So we know that about 68% of our data values happen to fall between one standard deviation of the mean. And then as you go 2 standard deviations from the mean, that represents about 95% of your sample. And going 3 standard deviations from the mean is going to represent basically all of it, about 99% of your sample. So it can be useful to kind of predict where people are at and kind of what your sample's made up of. So in addition to this, in addition to doing stats and whatnot, we can also organize our data by graphing it. So one of the most common graphs is what we use when we're looking at correlations. So again, correlations are when you look at the relationship between 2 different variables. We can plot that on what we call a scatter plot. So it illustrates with an x-axis and a y-axis where your data points fall for each of those 2 variables, and you can kind of infer a relationship. So for instance, on the left, we have baseball ticket prices. So across years on the bottom, as years increase, average ticket price happens to also go up. So by plotting each of these data points, you can kind of see the relationship. So it's a fun fact, positive correlation if you wanted to test yourself. And then the other example that I have here is time spent watching TV. So you see on the x-axis, the more hours of TV you watch, leads to a lower grade. So this is a negative association. It's a decreasing line. So scatter plot is just a nice graphical way of depicting correlations. Okay, so those were all descriptive statistics, ways that we can just kind of organize and be like, hey, I tied up in a bow, this is kind of what my data looks like, cool. Inferential statistics, though, are kind of the meat of the stats, the thing that like it is more informative. So inferential stats allow you to actually draw conclusions, draw inferences, and generalize what you've learned from your study with your sample to larger populations. Chances are that if you're, studying things like a clinical drug, you're not really just curious how it affects, the 10 people in your sample. You're really trying to find something that's going to help the general population. That's especially true nowadays if you think about the different research studies that are testing out COVID vaccines. They're testing it in random samples, but their goal isn't to just fix the sample. Their goal is to be able to generalize and find something that's going to be effective when applied to the general population. Inferential stats are the things that allow us to do that. So we're kind of in this cycle here where we have our population and we want our population to be representative in the sample that we choose. And that way, if we have a random assortment of people in our sample, think of all the different colored people as opposed to just purple and pink, that allows us to then make conclusions about the general population. So thinking back to this thing, we're basically asking ourselves, was there actually an effect? Once we've controlled for everything, we've randomly assigned our people to our groups, there are no other confounding variables that we need to keep track of. If we measure our dependent variables, are they different? Is there actually an effect of our independent variable manipulation? Now, in order to ask yourself, is there an effect or not, we need to compare it to something. So we compare it to what we call the null hypothesis, which you might see written as H sub naught, H sub 0. And this is kind of the default position, that there's no difference between these two measures. The groups won't be the same. It's kind of like playing devil's advocate. So like, pretend you're like really excited about your research question and you go up to your friend and you're like, look at my predictions, like, I'm super excited. And you're like, look, like an apple a day, like definitely keeps the doctor away, I'm studying this. And your friend is like, nah, like that's not true. That nah attitude, that's the null hypothesis. Nah, null, cool. It's that idea that there's nothing there, there's no effect. It's the boring hypothesis, the devil's advocate, thing we're gonna compare against. Now, in order to determine whether those two things, whether the null and our results are actually different, we need to rely on what we call the standard of statistical significance, which is what kind of this agreed upon value we all look to determine whether our effect is actually real, actually meaningful, actually not just due to chance. Because chances are, if you test a bunch of different people, for instance, their scores on a test or whatnot, and you give some groups caffeine and the other not, chances are, randomly, it's gonna work at least some percentage of the time. So the thing we're trying to ask ourselves are the results we got due to chance or likely actually real?